We were just discussing radar and simple radar, and now we'll discuss Doppler radar, which has the same components of radar on steroids. Okay, so with Doppler radar, instead of a single pulse of radio frequency, usually microwave frequency, that goes out and then comes back, you are talking about sending out multiple pulses at two different um, polarizations. What I mean by that is that you will have a vertical polarization, meaning poles, just like North and South Pole, a vertical polarization beam that goes out, and a horizontal polarization beam that goes out, so that you've got a pole on one side and on the other. And between the two of these same beams that go out and lock onto a raindrop or a hailstone or a snowflake and send it back, you can actually get the size of the precipitation that you're looking at in the cloud. So you can see if that water vapor that has just condensed is large enough to produce a storm with large raindrops, or if it's just water vapor that has just condensed and it's not going to become a rainstorm. And consequently, you can also see hail in there, and you can see snow as well. So Doppler is sent out many pulses, many angles, and two polarizations. It's called dual polarization for that. In terms of that, you can also look for the Doppler effect. And the Doppler effect is what you notice when a siren is coming at you. I work EMS, so this is my wheelhouse. And when I am driving and I'm putting the siren on, I'm very aware of who is in front of me, because that's going to be a very high-pitched siren with a very, very tight frequency coming at someone, like right here. Even though I am sending out the same frequency, it's getting smushed by the objects in front of me. And consequently, the same frequency that I'm sending out gets elongated as I move away from it. And so the people in front of me hear a very, very high-pitched siren, and the people behind me hear a lower-pitched siren. By looking at this in a cloud, you can see if the cloud is moving away from you or moving toward you. You can see if the winds are coming toward you or going away from you. And that can all figure into hurricane predictions, and especially tornado predictions. So Doppler is used to really predict severe weather, and it does it very effectively. The way it looks, as I said to you, the dual polarization, there is the vertical beam, and there is the horizontal beam that goes out that is trying to track the size of the precipitative wave. And from that, you can gather whether or not it's ice crystals or dry snow, or graupel, which is a grittier ice crystal, hail, heavy rain, large drops, but not heavy rain. It's very specific. So we have a Doppler Center at Rutgers. If you choose to study meteorology at Rutgers, they have a great setup there. And from that, you can also get, in Doppler radar, you can also get precipitation intensity. So not only the type of precipitation, but the intensity of the precipitation. The orange, of course, and the yellow is going to be more intense work than the areas that are up to light green. You see this is called a hook echo. We'll learn more about that when we learn about tornadoes. But you're looking for that hook shape. See that hook shape right there. So the intensity of the precipitation. And you can also look, and they can calculate totals and rates, rainfall rate from there. So you can look at the data and visualize it, and you can calculate off the data and visualize that as well. A great career for data visualization. Now, we can even get, from space, we can get Doppler-like measurements. These are microwave beams coming down from space satellites that are reflected back, and they can be moved into 3D angles. This is a weather satellite called the Global Precipitation Mission Satellite, put up earlier in the 2000s. That is looking at a hurricane and is actually verifying that there are bands in this hurricane that we suspect. It's kind of a rough model right here, but we're suspecting that hurricanes are actually groups of thunderstorms that move together. We'll get into that more with hurricanes. But when we talk about satellites, and I'm going to move this over, when we talk about satellites, we're talking about light information or information from light that is beamed down to the atmosphere and then reflects back up to the satellite and collects as data and then is sent down to Earth, and it's looked at for analysis. What you're looking at here is actually Doppler radar combined. So Doppler radars, remember, 160 of them across the US, about 3 per state, can be combined to make an entire image of the continental United States. This image up here is actually infrared imagery that's beamed down from the satellite and reflected back, and it is a wide range of infrared. So it is everything from near infrared to high energy infrared. So in doing that, this can track the temperature of storms, and especially right there, really hot right in the center. And we'll learn, and you've learned a little bit more about cyclonic action and the heat in the center. And also, when we get into the longer wave infrared, we're looking at some of the water vapor as well. So this is water vapor alone. And I think that you would really enjoy a video that I posted after this that shows these 3 synchronous images over the course of a year. So I think you'd enjoy that. See, this is Hurricane Irene, Hurricane Irene, Hurricane Irene, 3 different views. It's all data coming in from the same satellite. This is a cloud representation that you know of as GOES East, and it's very easy to track the visual of GOES East. This is the Doppler, which is the combination of all the Dopplers in the US. And this is the IR from GOES East. This is a broad range of IR, and this is a more targeted range of IR, just water vapor. Very cool stuff. When we look at forecast models from all of this data that's coming in, we have to compare it to the past when there was not much data coming in. This is actually an amazing weather map from 1893. And what is fascinating about this weather map is that these are the beginnings of station models. You see the circle in there. You're going to be learning more about the data in station models. And all they're reporting in here is cloud cover and wind direction and a bit of wind speed. I don't even think I see a clear marker for wind speed from the Beaufort scale. So I think we're only looking at wind direction and cloud cover here, and you have some temperature data in here, very little. There were approximately 50 to 60 weather stations across the entire United States in 1893, all connected by telegraph, and that was seen as a huge advance in tracking some of the aberrant weather across the United States, especially tornadoes. You could telegraph it across a warning. But as you can see, there's not a lot of data in here. So in order to make this map, which this is a 7-day map, it's quite amazing. It takes a lot of skill for a meteorologist to understand that this is based on his or her experience in persistent trends and persistent movements of air across what they knew as pattern recognition and what they knew from the climate of that area. This is in December of 1893. They already had an awareness of cold air moving down from Canada. Of course, they had no understanding of the jet streams that were bringing that down, but you begin to see it. You also begin to see the beginnings of a subtropical jet stream, although they had no understanding of what that meant. This is climatological patterns that they're forecasting from, just from experience and a little bit of data. Now, of course, this is an example of the meteogram data that collects data. These triangles are actual data. The green is all predictions. All right, and they are looking at a form of statistical prediction called an MOS, a Model Output Statistics program that they put this into. These are very well known, used in airports to use this model, MOS. For good or for better or for worse, they use the MOS model. And I should take this off of here, so I'll take this off in this slide in here. But this this model that we're talking about really tends to concentrate on trending data and on recognizing patterns. So there's a lot of experience involved in this model, along with the statistics that go along with it. So this is kind of a bridge to get us up to the National Weather Service models that are still used, but I'm taking you chronologically through this. When you get to these statistical models, you'll get statistics for probability of precipitation, which is known as POP, probability of precipitation, anywhere from 0 to 80%. And you're saying, well, what does that mean? And actually, it means that when you say there's a 20% chance of showers around the Randolph, New Jersey region, that means that anywhere in the region could have showers at that time. It doesn't mean that your particular location, your particular zip code has that percentage. It's the entire region. So this gives you a little bit of information about the wording that the National Weather Service uses. You could look over this in figure 9.9-2 in your text. It really helps you out a bit to understand the difference between scattered showers and chance of precipitation and precipitation likely, what that really means in terms of steady precipitation and showery precipitation. It's worth looking over. There are other types of experiential forecasts that deal in patterns. So one of the pattern forecasts besides, and these are called analog forecasts because they're so into the structure, the analog structure of patterns. So this is a probability forecast you see it all the time for white Christmases. So now we've talked about statistical forecasts. We've talked about analog forecasts based on experience. These are probability forecasts based on 30 years of experience right there for a white Christmas. There's other types like weather type forecasts. It's another pattern like you'd see here. In September, you're often thinking about the pattern of Santa Ana winds, Chinook winds around Colorado, and sometimes in September you'll get a real dip in the jet stream. So these are weather types, not specific weather forecasts at all, just very general. And then other patterns that are like weather types are climatological forecasts. A lot of farmers use these. The Farmer's Almanac actually bases their climatological long-range forecasts on the short waves and the long waves that are noted in the atmosphere. They were taking, obviously Farmer's Almanac goes back 200, 250 years. They were looking at some of the folklore, which goes back thousands of years, that notices animal patterns, insect patterns, taking some of that folklore and applying it to what they knew for shortwave and longwave patterns based on what they were seeing in the climate, and then they they could look out from there. They also used a lot of sunspot data in the Farmer's Almanac to get their climatological forecasts.